Hello, I'd like to welcome you to the second part of lecture 18. In this part, we'll start to talk about the common gate amplifier, which is shown here in this figure. And as you can see in this figure, we have the transistor here, and the gate is grounded. So the gate is really our reference here. So the input is applied at the source. This is the source. The input is applied to the source. So the input is applied between the source and the ground. So it's between the source and the gate. And the output is collected from the drain, between the drain and ground across this load resistor. So it's really the output is collected between the drain and the gate. This is why we call this a common gate amplifier, because the input is applied between the source and the gate. The output is collected between the drain and the gate. Of course, for this is a typical amplifier. We have to follow exactly the same steps that we did before for the common source and common drain amplifiers. We have first to find the operating point. We remove all these transistors, only carry the DC analysis, determine the current flowing in this circuit, determine the operating point, and this will give us the parameter GM, and then we replace this transistor by its equivalent AC small signal model. Consider all these capacitors to be short circuit, and then remove this source is now grounded, and then we do the AC part. And then if you do that, you'll end up with this expression here for the voltage gain, that the voltage gain is GM multiplied by the equivalent resistance here between the drain and the RL. And here I have a typo. There is no extra G here. This extra G is not there. Okay, so it is really GM multiplied by the parallel combination between RD and RL. So in other words, it is GM multiplied by the equivalent resistance connected between the drain and ground. Remember, at AC analysis, this is also ground. So this is here from drain to ground, this from drain to ground. So it is GM multiplied by this parallel combination, and the low input resistance of this one here, it is 1 over GM. Okay, as the book of Floyd does not really give a derivation for the gain of the common gate amplifier, I think it's very important to understand how we got this expression for the gain. So I will show you how this analysis goes. It's very simple. We'll assume now that we are only considering the AC circuit. So this is the AC circuit. As you could see here, we removed already VDD. All capacitors have been shorted out. Okay, the signal is applied at the input, is applied at the source. So between source and ground, or between the source and the gate, and the output is collected from the drain to the output here. This is from drain to ground, or between the drain and the gate, because the grid is grounded. So what we're going to be doing, we are going to simplify the circuit a little bit. This one here is in parallel with this one, as we mentioned earlier. Both of them are connected to the drain and connected to ground. This one is the gate, is grounded, and this one is the source. So we can redraw the circuit, make it a little bit simpler, and then apply the AC analysis. So after you simplify the circuit, this is how things look like. This is what I call here RD dash. RD dash is simply the resistance connected between the drain and ground. It's RD in parallel with RL for this example. We're going to replace the transistor by its small signal model. Small signal model is simply a current source flowing from the drain to the source. So it's a current source flowing from here to here. And then the current flowing in this current source, depending on the voltage VGS, this is G and this is S, but there is an open circuit between VG and S. So this is how things look like. This is VGS, and this is the current flowing here. And this is my input voltage Vn. So this is now is the source side, this is the drain side, and this is the gate side. And the gate, of course, is the ground, is the common between the input and the output. So if you take a look at this one here, you'll notice something very interesting. VGS is measured between this point and the ground, while Vn is measured between this point and the ground. Just to correct that, VGS is the opposite. It is ground relative to that point. It is ground, which is the gate, relative to the source. While Vn, it is this point relative to ground. So by taking a look at these two, you will notice that Vn is equal to minus VGS. This is very important for this calculation. The output voltage, what is the output voltage? The output voltage measured across RD dash is simply this current flowing here multiplying by RD dash. So it is GM VGS RD dash. What we can do, we can remove VGS and then replace it by Vn. Then you get this expression for the gain, for V out as a function of Vn. The gain by definition is V out over Vn, so it is Gm Rd dash, and this is the expression I mentioned to you earlier. It is Gm multiplied by the equivalent resistance, total resistance connected between the drain and ground. In our case here, it was Rd in parallel with RL. Now, if you want to determine the input impedance, I mentioned in the first slide that the input impedance for this common gate amplifier is 1 over Gm, which is not really that large, because Gm is about few milliamperes per volt. So this will give you maybe few hundred to few k input resistance, few hundred ohms to few k's. So here what we're going to be doing, and as for any structure that talks about input resistance, we have to get the ratio between the voltage, which is Vn, it's applied between the source and the gate, and the current being drawn from that source. So we have a voltage and there is a current. The ratio between the voltage to the current will determine the input resistance. So here we have one current flowing in, it is Gm VGS. We have one current flowing out, it is Vi over Rs, or I can simply replace Vi by minus VGS over Rs. So we have two currents flowing in. So I can simply write this expression that the current I flowing in is given by this expression. I is equal to this one minus Gm VGS and minus VGS over Rs. And these two minus signs because these two currents are assumed to be flowing to the node, while this one is also flowing in. This one is usually negligible relative to this one. If I replace VGS by minus VI, I get that I is equal to Gm VI. Then VI over I, the voltage to the current, is equal to 1 over Gm. Then indeed the input resistance seen by that small signal source is simply equal to 1 over Gm. So again, if you are sure about the configuration that this indeed a common gate amplifier, please go ahead and use these expressions that the gain is Gm multiplied by Rd dash, that the input resistance 1 over Gm. If you are in doubt about the configuration, I would say derive the expression for the gain from basic principles. Do a DC analysis, calculate Gm, and then go and replace the transistor by its small signal model, and then simplify the circuit, write V out as a function of Vn or V out as a function of Vthevenin depending on the circuit that you have. Okay, this is another example here, but this one is done using an enhancement type MOSFET. Again, it's the same analysis as we had earlier, but here I'm not asking you to do the DC part. I already have done the DC part. I reduced the circuit for you to just one resistance connected between the drain and ground, which is the gate, and then Thevenin equivalent for all the components connected to the source. This is the source, this is the gate, and this is the drain. Would like to find the gain of this circuit given that Gm is equal to 0.5 millisiemens, R Thevenin is equal to 50 ohm, and RL is equal to 100 kilo ohm. So for this one here, what we are going to be doing, of course, you can do it from basic principles. Replace this transistor by its small signal model and then try to get the ratio between V out to Vthevenin. This one way of doing it. Or I can simply use the expression I know from the common gate amplifiers that the gain is positive. It is Gm multiplied by Rd dash, and the Rd dash is simply what I call here RL. So don't get confused. It's whatever connected between the drain and the ground. The common ground, which is really the gate here in this case. So Gm is given to us, so the bias point have been determined for us. It's 0.5 millisiemens or 0.5 milliampere per volt. The Thevenin resistance is 50 ohm, and this RL is 100 kilo ohm. So the gain in this case is simply Gm multiplied by 100k, and this will give you V out over Vthevenin. And of course, Vthevenin may be a fraction of the source voltage. It's depending on the configuration, resistive configuration connected to the source. Okay, but here if you V out to Vthevenin, the gain is simply equal to Gm multiplied by RL. So the product of these two. Okay, as shown here, I simply said the Gm multiplied by RL. This 0.5 milliampere per volt. This is 100k, so 10 to the power 5. Then the gain is equal to 50, and the gain by definition here is V out over V Thevenin. But as I mentioned earlier, V Thevenin was obtained by replacing everything connecting the source by its Thevenin equivalent. But there may be another AC source and maybe a resistive network of some sort. So V Thevenin says 0.99 V source. You will see that the gain is reduced a little bit to 49.5. So this is how you can analyze common gate amplifiers. They give very good gain, but they have low input resistance. So maybe combining a common gate with another type of amplifier will give us a much better amplifier configuration. Okay, the last thing I would like to mention about these amplifiers is the cascode configuration. Cascode configuration, if you take a look at it, here we have an amplifier. This is a common source. Why it's a common source? You can see there is a resistance connected between the source to ground, but shorted by a capacitor. So for AC analysis, this becomes short circuit, so the source connected to ground. So we apply the signal at the source and then we collect it from the drain. But we don't collect it from the drain of the same transistor. We collect it from the drain of another transistor. And this transistor is actually a common gate. Why is it a common gate? Because you can see for AC, this capacitor becomes short circuit. So this is connected to ground. Okay? And the output is collected from the drain of that common gate amplifier. So for this common source amplifier, this part here replaces the drain resistance that we used to have before. We used to have a drain resistance RD. And for this common gate amplifier, this transistor replaces what we called R source. So these two are actually two cascaded amplifiers. It's called cascode configuration. It's a common source amplifier connected to a common gate amplifier. The reason why they use this one, number of reasons. First, it supplies, it corrects the problem with the common gate. The common gate gives very high gain, but the input resistance is low. While here, this is a common gate, but you see only the input resistance into the gate of this transistor, which is very high. So this is why you have a very high input resistance. The gain of this configuration, of course, you can do the complete AC analysis, do first the DC part, determine the current flowing, and the current, if you take a look at the current, this current will flow from here through the first transistor and then through the second transistor to the same current flowing in both of them, the same IDS flowing in both of them. You can determine, of course, GM1 here, GM2 here, replace every transistor by its small signal model. This one here is an inductor. At high frequency, it represents significant impedance. But while at low frequencies, it represents short circuit. So for DC, this is represented by short circuit here. This configuration is used in high frequencies. It offers wide band. I'm not going to go into the proof of this. Any one of you is interested, you can do the AC analysis, replace each one of these by its small signal model, try to find the expression for V out over Vn. The book of Floyd gives this expression. It's simply the product of the two gains. I'm not gonna worry about this derivation that much. If I give you an expression like this one, I will ask you to derive everything from basic principles. But this may take very long time. So I would say you should know about this configuration. It is very useful configuration. It offers very high input resistance and high gain, and it works over very wide band. There is a reason for that. It's called the Miller effect. We do not really discuss that much, but it's simply there is a cancellation of the capacitances that reduce the high frequency gain. So this can be a very high frequency amplifier. There is good insulation between the input and the output because the input is applied to one stage while the output is collected from another transistor. It's really a common source cascaded with a common gate. This is all what I wanted to know about this expression, and the expression for the gain and the input resistance is supplied in the book Floyd. You can derive both, but it will take you probably 1 hour. You draw the AC signal and so on. So what I want you to know, just to know about this configuration, that it does exist, and you know the expression for the gain. We may be able to use it in some of the examples.